the stator starter, the first primary resistance starter. Here some set of resistance are added in series with the stator winding. It is very simple starter, and during starting time maximum resistance is added, and during running time resistance and all it is cut out, and minimum resistance or zero resistance the stator winding. Okay, and X is the fraction with which the resistance value is added to the stator winding. So during starting condition X will be less than 1, and during running condition X is equal to 1. X less than 1 means some fraction of resistance is added to the stator winding. So this is the point X in this example. Okay. And during the running condition, the resistance and all it is cut out, and this is brought down here, and this knob is brought down. This knob is brought down here. In this case, your X value becomes 1. So it's a very simple starter, but the power loss will be there because resistance simply we are adding it, so little copper loss will be there, and because of that we have little reduction in the efficiency. In order to overcome this problem, in order to avoid this copper loss problem, people have replaced this resistance with the inductance. So that is the primary reactor starter. Concept remains the same. Stator resistance starter, similar to stator resistance starter. But the power loss will be very much minimum when compared to the primary resistance starter. Of course, every inductance will have a very minimum resistance, but the resistance value is very smaller than the inductance value in primary reactor starter. So because of this, the copper loss will be minimum when compared to the primary resistance starter. In these two starters, any doubts anybody is having? It's a very simple starter. Only some resistance is added and reactor is added. So that is the primary resistance starter and primary reactor starter. So from these two starters, what we infer? The motor starting current reduces by fraction X times of short circuit current, because some fraction of the resistance or some fraction of the reactance or inductance, it is being added to the stator winding. So the motor starting current reduces by fraction X times, and the line current also reduces by same times as that of motor current during starting. If you see here, this is the line current. The current which is flowing in this terminal, it is the line current, and current which is flowing in this terminal, that is the motor current. Okay, so this is the line current which is flowing here, that I have shown in red color. This is the line current which is flowing in the input side of the starter, that is the line current, and this is the motor current that is flowing in the output side of the starter. So that is what here we are saying. The motor starting current and motor line current, it reduces by the same amount. X times it reduces. The starting torque reduces by square of X. So how it is, you have to see from this equation. You see here, the starting torque relationship is X squared ISC by IFL the whole square into full load slip into full load torque. You see here, during starting, X is less than 1. During starting, X is less than 1. Since X is less than 1, the starting torque reduces by X squared time. Right? So that is the inference we are obtaining from the primary resistance starter and primary reactor starter. See here, we are reducing the starting current, that is advantage to us, but the starting torque it is reducing by square times s. I told you that if the starting torque reduces at one point of time, the motor refuses to start itself. So that is the demerit in this starter. The starting torque reduces by square of x. If the starting torque reduces at one point of time, the motor refuses to start, because every motor should have minimum starting torque. If it is not having any starting torque, then at one point of time the motor refuses to start at all. So the current is reducing, that is advantage to us, but the starting torque it is also reducing by square of x term, that is little demerit to us, but the advantage, what is the advantage? Current reduction, that is overcoming the disadvantage. What is the disadvantage? Torque reduction. So the last point, it doesn't matter here. The last point, it doesn't matter here, because this is coming than this. So the current is reducing, that is major importance to us. The torque is reducing little, the starting torque is reducing little, but that disadvantage, it is not much important when you compare with the advantages of these starters. So any doubt here? So always every system, if you propose, the system will have advantages and disadvantages. So you have to look at the advantages and compare to the disadvantages, right? So the next starter is auto transformer starter. That is the next starter. So first we have seen primary resistance starter. Second we have seen primary reactor starter. The third one is auto transformer starter. So this auto transformer starter, it is very much similar to the primary reactance starter. This auto transformer starter is very much similar to the primary resistance starter. The only difference is that in the primary reactor starter, it is very much similar to the primary reactor starter. The only difference is that in the primary reactor starter, these terminals are left open as such. That is the primary reactor starter. But in the case of auto transformer starter, all these terminals, it is connected together. So if you connect all the N terminals of primary reactor starter, then it becomes auto transformer starter. So that starter only, here it is shown with the switch. So during starting condition, maximum reactance is added to the motor winding, and during running condition, so this is your starting condition. So this switch, it is double throw switch, or in other words, it is called as changeover switch. So it is connected here. That is the starting position. You see here all the ends, it is connected together. The reactance end, it is connected together. So that is the auto transformer starter. So during starting time, during starting time, it is connected like this. So during starting time, it is connected like this. This and this and this. So during starting time, 2, 4, 6, these three terminals, it is shorted. So if you connect 2, 4, 6, then the X value of reactance, it is being added to each winding of the three-phase induction motor, so that the starting current get reduced. And during running condition, the terminals are connected like this. The terminals are connected to 1, 3 and 5. This is the terminals for running condition. 1, 3, 5. Right? It is very simple concept. During starting condition, maximum value of reactance is added to the stator winding. During running condition, no reactance is added to the motor winding because the switch is there to regulate the current. So this connection can be done either using some mechanical switch or by using any switch you can do this connection, right? So that is nothing but your auto transformer starter. Here the stator winding is connected in star form and auto transformer starter is connected in star form. So if you connect all these three terminals, it becomes star connection. You see here, this is first reactor, this is second reactor, this is third reactor. So if you connect all these three terminals, it becomes star connected auto transformer. And stator also it is in star connection. Auto transformer also it is in star connection. If you want, you can do delta connection also. Delta connection means this should come here, this should come here, and this should be connected here. So delta connected auto transformer also you can realize. So the concept is very simple in auto transformer starter. If you connect primary reactor starter either in the form of star or in the form of delta, depending upon the requirement and application, then it becomes auto transformer starter. So generally, if motor stator winding, if it is star connected, to make it uniform, to have symmetricity, the auto transformer starter also it is connected in star form. If the motor winding, if it is connected in delta, so to maintain the uniformity, the auto transformer starter also it is connected in delta, just to maintain the symmetricity. Or any special requirement is there or any special application is there. So for that also you can have either star or delta connection. So what is the advantage of auto transformer starter? Sir, first you have used primary resistance starter. So their power loss is more. Yes, of course, because you are adding some extra resistance. So definitely it enhances the copper loss little, that leads to the reduction in the efficiency. That is very clear. Then people have gone for primary reactor starter. Reactance, of course, the resistance is very smaller when compared to the reactance. So here the power loss is very much reduced when compared to the primary resistance starter. Next, the auto transformer starter also it uses inductance only. Here also there is no power loss. Power loss is very minimum as similar to the primary reactor starter. But what is the advantage of using auto transformer starter? That advantage you can see from this diagram. You see here, so the diagram with the switches, it is simplified like this. You see here, this is your motor winding, the three-phase winding, R, Y, B. This is your motor winding, stator motor winding, and this is your auto transformer starter. This is your auto transformer starter. You see here, you have the reactor 1, 2, 3, and here the reactor it is connected in star form because the motor stator winding it is connected in star. Okay, so this is your equivalent circuit of the previous diagram. So here you have the auto transformer starter and here you have the motor, right? And here if you see certain derivation, you look at this derivation. What is the auto transformer turns ratio? Auto transformer turns ratio, if you want to write in terms of current, it is I1 by I2. You take this current is I1. This current is I1, and this current, the current which is flowing in the motor winding, the current which is flowing in the motor winding, let me take I2. So I1 is the line current or supply current, and I2 is the motor current. Okay, I2 is the motor current. So what is the auto transformer turns ratio? Auto transformer turns ratio, no? X is nothing but I1 by I2. I1 is the input current to the auto transformer, that is the line current, that is the starting current, and I2 is the output current from the auto transformer, that is the input current to the motor. Right? And different notation here people have used. This I1, no, that is denoted as I starting current supply. I1 is denoted as I starting current supply, and I2 is denoted as I starting current motor. Okay, and what is my I starting current supply? I starting current supply from this equation, I can write X times ISC motor. Okay, I starting current supply, you just cross multiply it, I will get X times ISC motor. X times ISC motor. Okay, and here what is my ISC motor? What is my ISC motor? ISC motor is nothing but X times your short circuit current. The very earlier derivation we have seen. What is my ISC motor? ISC starting current of the motor is nothing but, if you use starter, it is X times short circuit current. So you substitute here ISC motor, you replace with X times ISC. So ISC supply becomes square of the current. So ISC supply is nothing but X squared of short circuit current. So now what is the final conclusion? If you look at the final conclusion from this diagram, or from this analysis, or from this equivalent circuit, I can write like this. If you see here, my starting current of the motor, it becomes X times ISC, right? But my starting current of the supply or line, anyway you can call, starting current of the supply or line, it becomes X squared of ISC. When you use auto transformer starter. When you use auto transformer starter. So what we understood from this simple derivation, the motor current, starting current, it gets reduced by X times, but the motor drawing the current from the source, that is getting reduced by X squared terms of ISC. Right? That is getting reduced by X squared terms of ISC. 1 minute. So when we use auto transformer starter, the motor starting current is getting reduced by X terms, but the motor supply or line current, it is getting reduced by X squared term, X squared times, right? So that is the biggest advantage when we use auto transformer starter. See, actually the motor, no, it is acting as a load to the supply line. You are connecting motor to the supply only. The motor starting current, it is reducing by X times, but the current which is drawing from the supply, that is getting reduced by x squared term. It means that you are not much loading the supply line using your motor. So that is the another advantage of your auto transformer starter. So when we use auto transformer starter, the motor starting current is getting reduced by x times. In addition to that, the motor line current or the supply current is getting reduced by x squared times. That is the greatest advantage when we use auto transformer starter. But earlier case, if you use primary resistance starter or if you use primary reactor starter, the motor current also it is getting reduced by x times, and the line current also is getting reduced by x times. Right? That is okay, fine. But when you use auto transformer starter, it is giving more advantages with respect to the supply side, with respect to the grid side, with respect to the transmission line side. So that is the advantage of using auto transformer starter. So that is why in all the industries, to start the induction motor, auto transformer starters are highly preferred. Right? So you see here, these are all the inferences. The motor starting current reduces by fraction x times of short circuit current. The line current reduces by square of x. And of course, the starting torque, it is getting reduced by square of x. So that you cannot avoid it. Any doubt here? If you are having any doubt, you can ask me. So first, the resistance people have used to overcome the loss problem. Reactor people have used, and in order to have more advantages with respect to the transmission line side, people have used auto transformer starter. The reactor starter, either it is connected in star or it is connected in the form of delta. That's all. So if we do that, the line current is getting reduced by square of x times. But of course, the starting torque it is getting reduced by square of x. That you cannot avoid in primary resistance starter, primary reactor starter, and auto transformer starter. Shall I proceed further? Difficulty in understanding, you can ask me. Shall I proceed further? Okay. So now, so we have added some starter to the input side of the motor, and we try to reduce the starting current. And of course, when you are doing this, the starting torque also it is getting reduced by x turn. All these things we have seen till now. I hope you would have understand all these points. So with that, I proceed further. Now, instead of using separate starter, right? Instead of using separate starter for the induction motor, people thought that why can't we use the stator winding itself to act as a starter? Right? Instead of adding separate starter circuit to the stator, you see here separate circuit is added. So this is your auto transformer starter is added to the stator winding. Similarly, the primary resistance starter separate circuit is being added to the stator winding. People thought that instead of having separate circuit, why can't we use the stator winding of the motor itself to act as a starter, so that it reduces the circuit complexity. So that type of starter is called as star delta starter, right? So this is very simple, and the starter, no, it came from the intelligent thinking of the people. You see here the motor stator winding itself, first it is connected in the form of star, right? So the motor stator winding itself, first it is connected in the form of star. It means that during starting time, the motor stator winding, it is connected in the form of star, and during running time, using some switch, the same stator winding of the motor, it is connected in the form of delta. So when you do this, what is happening to the motor? When you have star connection, what is the advantage? The voltage, it is getting reduced by √3 times. So √3 times reduced voltage only is being applied to the motor winding, because each motor winding, V by √3 only is applied. That is the phase voltage, the line voltage is V, that is the line voltage. And what is the voltage applied to each phase of the winding when you have star connection? V by √3. So when the stator winding, it is in the form of star, the voltage is reduced by √3 times. The reduced voltage is being applied to the machine during starting time. So because of that, the starting current is getting reduced. And during running time, the star connection, it is connected in the form of delta. Delta, the line voltage is equal to the phase voltage, right? Because during running time, the use of starter is not needed because the slip is coming into picture. So during running time, the star connection is changed to delta connection. So the full voltage is being applied to the machine during the running condition. So this is called as star delta starter. So that is what I have written here. No separate starter is required. The stator winding of the motor itself initially or during starting connected in star, so that the applied phase voltage to the machine gets reduced by 1 by √3 times. The starting current can also be reduced. After some time, during running time, the stator winding is connected in delta. The changeover of connection from star to delta can be done using switch. So the line current in star is 1 by 3 times of line current in delta. So because of this reduction in voltage, the current also is getting reduced, right? So this is the diagram. So you have the motor stator winding terminal 1 dash, that is R phase, and 2 dash, that is Y phase, and 3 dash, that is B phase. You have all the 3 windings, you have the terminals 1 dash, 2 dash, 3 dash, and the supply is being given to the 3 windings. And during starting condition, this switch, it is connected here. So if you connect this switch to this point, this is the starting. So if you connect this switch to these points, then the winding, it is connected in the form of star. And when you connect this switch here, then the winding will be connected in the form of delta. So 1 dash, 2 dash, 3 dash, that is for star connection, and 1, 2, 3, that is for delta connection. Of course, this is the squirrel cage rotor. And this switch, is called as triple pole double throw, because it is having 3 poles for 3 phase. This is pole 1, pole 2, pole 3. So the switch is having triple pole, double throw. You can throw to this side or you can throw to that side. So triple pole, double throw switch. In short, it is called as TPDT switch. Right? In short, it is called as TPDT switch. I think this switch is available in our lab. I have to check. If you come, you can see this TPDT switch. Triple pole, double throw switch. And this is a mechanical switch. Using this also, you can have the changeover from star to delta. But nowadays, no electronics have come up. You can use electronics methods also to change the switch from one position to another position. So this starter is clear to all. Any doubt, ask me. So we have seen primary resistance starter, reactor starter, auto transformer starter, star delta starter. 4 starters we have seen today, and all these starters, no, it is called a stator side starter. If you have any doubt, you can ask me. Otherwise, we can wind up the class today. We will meet in the next class.